want to go ahead and find all those 8 things for this particular problem up here. We're going to find your x-intercept, and that's when your y is 0. Plugging in or setting it equal to 0, you get 0. Your y-intercept is when x is 0, so you plug in 0, you also get 0. So it crosses at the origin. It's the only spot it crosses our axes. We're going to take a look at the end behavior. You want to be concerned about the end behavior when you're looking at your horizontal or oblique or slant asymptotes. What happens is you go far to the right and far to the left. That's at your limit as x approaches plus or minus infinity. Well, in this case, the 2 is going to have really no effect when this gets really big. So it's really just the square root of x squared, but it's a positive in front. So the bottom's always positive. So you take a positive number, plug it in here. You get the top and the bottom both being the same, so you get a horizontal asymptote of 1 as you go far off to the right. However, when you plug in a big negative number, the top becomes negative and the bottom becomes positive because of the absolute value. They're the same value but of opposite signs, so you get a horizontal asymptote going to the left of y equals -1. We'll go ahead and we'll find our first derivative. Here's our first derivative. You'll notice that with our first derivative that we have no critical points. It's never equal to 0 because 2's on top. No variables are on top. It's never undefined because the bottom is never equal to 0. So that means your function is either always increasing or always decreasing. Now, we can just test a point. Easiest one to try is 0. If you plug in 0, you end up getting a positive, which means your function's always increasing. Now, if your function's always increasing, you have no max and no mins. We then go ahead and take a look at our second derivative over here. Taking a look at our second derivative, it does have critical points. Yes, the denominator will never be 0. However, the top could be 0. What causes the top to be 0? Well, our top would be 0 at x being 0, so we have a critical point of x being 0. So for our second derivative number line, we're going to have to put x being 0 on our number line, check a number on each region, check a number to the left of 0, plugging it into your second derivative because we're looking at concavity. Plug in a number to the left and we get positive, which means it's concave up. Trying a number to the right of 0, plugging it into your derivative, you end up getting a negative, which means it would be concave down. Since our problem is switching from concave up to concave down at 0, that means we would have a point of inflection. Well, how do we figure out the y-coordinate when we're looking for a point on our graph? Well, then you have to plug it into your original function. Take 0, plugging it into your original function, and we end up getting 0. So the point of inflection is the origin. When we go ahead, plot our point of inflection, our horizontal asymptote to the right, our horizontal asymptote going to the left, we know we're always increasing. We also know that we're concave down over here, so we're going to be like this, and we'll be like this. Now, instead of being always increasing, or another way to do this, if you were always increasing but didn't know your concavity, would be to have it like this here. But our concavity lets us know we cannot have this red graph. So our concavity allows us to be able to go ahead and get an accurate graph of what's going on here. For the next problem here, since this is a trig function, it ends up being periodic. Since we only have 1's in front of your x's for your sine and your cosine, we know it's going to repeat every 2 pi. So let's just go ahead and look at our graph of this and analyze our graph for one full period. we're going to go ahead and try to go from negative pi over 2 to positive pi over 2, but not including the endpoints. We're not going to include 3 pi over 2 because that would cause us to get a sine of 3 pi over 2, which is a negative 1 plus 1, cause us to get a 0 on the bottom. So that lets us know we have a vertical asymptote at 3 pi over 2. Same idea with a negative pi over 2. It would be a vertical asymptote. So our domain is everything except where our vertical asymptotes are occurring. So now we'll go ahead and we'll look at our derivatives. Derivative, our first derivative is this right here. Now, we don't really have any critical points. Since we have no variables on top, our derivative will never be 0. The bottom will be undefined at some points, but never on the interval between these two numbers. It'll be undefined at each one of these numbers, but remember, we're looking at what's between here. So we have no critical points. So your function's either always decreasing or always increasing. In this case, we know it's always decreasing because if we try any number, plugging it in here, we get a negative. So we know our function's always going down. So then we'll go ahead and we'll look at our second derivative. Our second derivative, we need to look for our critical points. Since we have a variable on the top, we could have a critical point at what causes the top to be 0. So you set the top equal to 0, when is cosine equal to 0, and that's when x is 0. Well, we also need to look at our critical points for where we're undefined. Oh, I had said this wrong. When cosine of x is 0, that means you're at pi over 2 for your angle. And it's undefined at these endpoints, but we're only concerned about what's going on in between those two because we know those two endpoints are our vertical asymptotes. So we're going to check a number in each region. So we try a number between negative pi over 2 and positive pi over 2, plugging it into our second derivative because we're checking concavity. And we end up getting a positive, so we know we're concave up. Over here, try something between positive pi over 2 and 3 pi over 2. We get a negative, so we know we're concave down. Since we are switching concavity, we know we have a point of inflection at pi over 2. And how do we figure out the y-coordinate? We have to plug that pi over 2 into your original function at the top up here in black. When you plug in pi over 2, we end up getting our y-coordinate being 0. We had talked before how your period is pi over 2. Your x-intercept is where you set your original function equal to 0 and solve it. Your y-intercept, you plug in 0 for your original function. Vertical asymptotes, we talked about those already. There is no horizontal asymptote. There is a point of inflection. When you go ahead and graph all that, we'd have our vertical asymptotes that we talked about. And we're really looking only at what's going on in between these. We do our vertical intercept. We do our x-intercept, which happens to be our point of inflection. We knew we were always decreasing, so we knew we'd have to come from the upper left to the lower right. We also knew between 0 and negative pi over 2 you were concave up. We also knew between pi over 2 and 3 pi over 2 you were concave down. Being periodic, you're going to take this here and repeat it over here and going off to the left.